As we go through the examples, please notice how each example will follow these 7 steps. Example 1. How fast does the radius of a spherical balloon change at the moment when the radius is 1 centimeter? If the air is blown into it at the rate of 10 cubic centimeters per second. Write every given rate as a derivative with respect to time. This is a rate. Cubic centimeters is what we measure volume in. So this number is the derivative of volume with respect to time, because seconds is what we use to measure time. That's the given rate. Then we look for a rate to be found, and we'll be writing something that looks just like that. Here's a rate to be found. How fast does the radius of the bubble change? Radius. So the derivative of the radius with respect to time is what we're asked to find when the radius is 1 centimeter. Okay, then we're going to write a formula. That's where we are. The volume of a sphere is 4/3 pi r cubed. That's the formula. Eliminate variables if possible. This step is not relevant in the problem we're doing. So we're up to here. Differentiate implicitly with respect to time. Differentiate means take the derivative. The derivative of the left side with respect to time equals the derivative of the other side, which is this exponent times this number. 3 times 4/3 pi is 12/3 pi. And then this becomes r to the second power. And we have to remember to multiply by the derivative of what's in the parentheses with respect to time. This last part is called the chain rule. So that's that. Now we're going to plug in numbers and then solve for the unknown rate. So the numbers to plug in are up here. dv dt is going to be replaced with 10. The r is going to be replaced with 1. And dr dt is what we're trying to find. So we're going to solve for dr dt. 10 over 4 pi, which can be reduced to 5 over 2 pi. Since the radius of this sphere will be measured in centimeters, and time in this problem is measured in seconds, this answer will get labeled centimeters per second. Okay, in this example, how fast does the water level drop when a cylindrical tank of radius 1 meter is drained at the rate of 3 cubic meters per second? Since cubic meters is used to measure volume, this given rate is the derivative of the volume with respect to time. That's seconds is time. And because water is draining, this derivative is a negative number. The volume is getting smaller at a rate of 3 cubic meters per second. the rate that we have to find is how fast does the water level drop. We'll use h for the level of the water, or the height of the water. That's the rate to find how fast does the water level drop. The volume of a cylinder is pi r squared times h. In this cylinder, with a radius of 1 meter, the volume of water, no matter where the water is, no matter what level the water is, the radius of the water is going to be 1. It does not change. So the formula is V equals pi h. This represents the volume of the water in the tank. Differentiate both sides implicitly. The derivative of the left side with respect to time. The derivative of the other side is going to be pi times dh dt. And now where the dv dt is, we're going to put -3. And where dh dt is, we're going to put dh dt. And then solve for dh dt. -3 over pi. Since h, that's the level of the water, is measured in meters, and t is measured in seconds, this number is -3 over pi meters per second. Example 3, a ladder 26 feet long rests on a horizontal ground, here's horizontal ground, against a vertical wall. This is the ladder leaning. It's a 26-foot long ladder. The foot of the ladder, here's the foot of the ladder, is being pulled away from the wall at a rate of 4 feet per second. Let's call this side of this triangle x and this vertical side y. This is a given rate. That's the derivative of x with respect to t. How fast is the top of the ladder? Up here, this is the top of the ladder. How fast is the top of the ladder sliding down the wall? So the rate to be found is dy dt. When the foot of the ladder is 10 feet from the wall. When the foot of the ladder is 10 feet from the wall. Now, note before we do any calculus that at this instant when x is 10, y is 24. When x is 10 feet on this triangle, y has to be 24 feet. If you don't know how we got this, please ask me about it in class. Hint, this is not calculus. So the next step in that list of steps is to write a formula, which in this case is x squared plus y squared equals 26 squared. No matter where this ladder is, this will be a true statement. It's called the Pythagorean theorem. Now we're going to differentiate implicitly. The derivative of 1x squared is 2 times x to the first power times the derivative of x with respect to t. By chain rule, we have to remember to multiply by the derivative of what's in the parentheses. With respect to t, the derivative of the next term is 2 times 1 times y to the first power times the derivative of y with respect to t. That is again the chain rule. And the derivative of 26 squared is 0. because 26 squared is a constant. Now where the dx dt is, we're going to put 4. Where the dy dt is, we're going to put dy dt. Where the x is 10, where the y is 24. Because we know dx dt is 4 feet per second. And when x is 10, y is 24. And we're trying to find dy dt. That's how fast the top of the letter is sliding down. We're trying to find that rate when x is 10. After the step called plug in numbers, we solve for dy dt. So 80 plus 48 dy dt equals 0. 48 dy dt equals negative 80. Dy dt equals negative 80 over 48, or negative 5 over 3. And y is this distance from the top of the ladder to the floor, and that's measured in feet. And time down here is measured in seconds, so negative 5/3 feet per second. And do you know why this answer is a negative number? Even though dx dt was a positive number. Why is that? Example 4, water runs into a conical tank at the rate of 2 cubic feet per minute. Cubic feet is volume. So the derivative of the volume with respect to t is 2 cubic feet per minute. That's a rate that is given. The tank stands point down and has a height of 10 feet. And a base radius of 5 feet. How fast is the water level rising? So in this tank, there's a level of water, which we're going to call h. The h dt is the rate at which the level of the water is changing. How fast is the water level rising when the water is 6 feet deep? The volume of a cone is 1/3 pi r squared, h. Now, one of the steps in the list that we haven't used yet, I'll go back and look at the steps, is eliminate variables, but do not eliminate variables mentioned in the first 2 steps. What that means is, in this problem, we have 3 variables. We have v and r and h, but we only want v and h. R is not mentioned up here in our previous setup. And the way we eliminate the r, we have to eliminate the r because it's not up here, is with similar triangles. Inside this cone, you could draw a triangle showing that the height is 10 feet and the radius is 5 feet. That's the tank. But in the water, or in the tank, there's water that goes up to some height, which is changing, and the radius of the water will be changing as the water runs into the tank. But these 2 triangles are similar, which means corresponding sides are in proportion. 5 is to r as 10 is to h. These are corresponding sides of similar triangles. Since 5 over r has to equal 10 over h, that means 5h has to equal 10r. So 5h divided by 10 equals r. That means the r in this formula can be replaced with h over 2. This can be reduced to h over 2. The volume of the water in the tank is 1/3 pi h over 2 squared times h. Or the volume of the water in the tank is pi h cubed over 12, because h squared times h is h cubed, times pi times 1 is up here on top. 2 squared is 4, and 4 times 3 times 1 is 12. That's the same as pi over 12 times h to the third. The derivative of v with respect to t is this exponent times this number, 3 times pi over 12, which is 3 pi over 12, or pi over 4, times h to the second power times dh dt. This times dh dt is the chain rule. We say don't forget to multiply by the derivative of what's in the parentheses. Now where dv dt is, we can put 2, and where h is, we can put 6. And dh dt, we're going to solve for that. So 2 equals, this is 36 over 4, which is 9, times pi, times dh dt. Solve for dh dt, 2 over 9 pi. And this is the h, that's the height or level of the water. It will be measured in feet. Down here is t for time, which is measured in seconds. Two over 9 pi feet per second. And we have one more example. A balloon is rising from the ground at 140 feet per minute, is tracked by a rangefinder at point A located 500 feet from the point of liftoff. So here's the point of liftoff, and there's a balloon rising. We'll call this distance y, because it's changing as the balloon rises. And this given rate is the derivative of y with respect to t. There's a point A that's 500 feet from the point of liftoff. From this point, find the rate at which the angle at A and the range r, by that they're talking about this distance on this hypotenuse. Find these two rates when the balloon is 500 feet from the ground. Find the rate at which the angle is changing. And there's another problem. It's also find the rate at which r is changing. We have to find both of these when the balloon is 500 feet above the ground. That's when y is 500 feet. So there's actually two problems here. To answer the first part, we're going to use this formula. We're going to say the tangent of this angle is opposite over adjacent. The tangent of an angle in a right triangle is opposite over adjacent. And now we're going to differentiate both sides. The derivative of tan A is secant squared A, don't forget the chain rule, times the derivative of A with respect to time. And the derivative of 1 over 500 times y is 1 over 500 times the derivative of y with respect to t. Now, a couple things to note about this triangle here is when y is 500, the triangle looks like this. This point A is stationary at 500 feet from the point of liftoff. The y is changing, but when y is 500, this hypotenuse can be found to be 500 radical 2. You should use the Pythagorean theorem to see how I got that. So when y is 500, the cosine of this angle is adjacent over hypotenuse. Cosine of an angle in a right triangle is adjacent over hypotenuse. So the cosine of this angle is 1 over radical 2, which means the secant of this angle is the square root of 2 over 1. So right here, when we get to the step called plug in numbers, where it says secant squared A, we can put 2, because this is the secant of A. The secant of A squared is 2. dA dt is what we're trying to find. Copy all this. And we know dy dt is 140. And now we're going to just multiply both sides by 1/2 because we're solving for dA dt. dA dt equals the number over here, which is 140 over 500. We're multiplying by 1/2 because I multiplied this side by 1/2. This can be simplified right here to 7 over 50. The angle in this triangle will be measured in radians, and time is measured in minutes. I think it was minutes. So the answer is 7/50 radian per minute. That's the rate at which the angle A is changing with respect to time. To find dr dt, instead of using this formula, we'll use 500 squared plus y squared equals r squared. In this triangle, this will always be true, no matter where the balloon is. So we'll differentiate. The derivative of 500 squared is 0. The derivative of y squared is 2y to the first power times the derivative of y with respect to t. The derivative of r squared is 2 times r to the first power times the derivative of r with respect to t. So we're trying to find dr dt when y is 500 feet. And we know that dy dt is 140. And we also know that when y is 500 feet, r is 500 radical 2. Two times 500 times 140 divided by 2 times 500 radical 2 equals dr dt. Divided both sides of this equation by 2 times 500 radical 2. And this simplifies to 140 over radical 2. And if we multiply the numerator and denominator by radical 2, we end up with 70 radical 2. And the r in this triangle is measured in feet. That's feet. That's minutes. 70 radical 2 feet per minute. That's the rate at which the range of this hypotenuse is changing with respect to t.